All right, so we saw taking the derivative of e to the x, which is a very special exponential function, and we saw how to take the derivative of ln x, which is a very special logarithm. So today we're going to talk about just generic logarithms and exponential equations and how we do that. But first, let's try to differentiate the function I've given to you below. So we zoom in, and we want to find this derivative. So you can see it is going to be a chain rule. So bring that 4 down in front. Leave what's inside the bracket as is. Subtract 1 from my exponent. And now I have to times it by the derivative of what's inside the bracket. So the derivative of 1 is going to be 0. So it'll be 0 plus something, so I'm not going to write it. So now we need to find the derivative of 5e to the negative 10x. Okay, well, it says that we just kind of write the function as is. And then we times that by the derivative of the exponent. And now we can just try to clean this up a little bit. So I'm going to write down my first part, which doesn't need much cleaning up. Well, except for this 4, pardon me, that 4 and that minus 10 and 5 at the end can actually all come together to simplify down, because that 4 is outside of the bracket. So if I look at all my constants, 4 times 5 is 20, times minus 10 is minus 200. And then I'm going to write down that e to the negative 10x out front, and then I'm going to write my bracket. It doesn't really matter order of multiplication. So what mathematicians like is having our constant out front, and then we have any kind of like smaller function, which is just e to the negative 10x, and then any brackets. So there is my derivative. Okay, so here are my new theorems. So for an exponential, if I have some generic y equals b to the power of x, then the derivative is b to the x, so keeping my function, and then timesing it by the ln of b. Or the bigger one, so b to the g to the x, so my exponent just isn't x. Then my derivative is, write down my general equation, b g to the x, then it's going to be ln b times the derivative of whatever my exponent is. So let's look at some of these here. I know that looks really, really confusing. And that what I have is f at x equals 3x. So my f prime at x is equal to, keep it the same, times it by the ln of my base times the derivative of the x, which is 1. So really it is probably more the one up here, again, where it's just b to the x, but I almost like to forget that one there because there's no difference. If my derivative is just x, then g prime at x is just 1. So I like to kind of just memorize it as always timesing it by the derivative of my exponent. So if my function is 3 to the power of x, then my derivative is 3 to the power of x times the ln of my base, which is 3, times the derivative of my exponent, which is 1. So I get 3x times ln 3 times 1. All right, and then just cleaning that up, there's really not much I can clean up other than the fact I did that times 1, which I don't need. So 3x ln 3. I don't need to worry about ln, oops, that looks like ln to the power of 3, sorry. I don't have to worry about ln 3 is. Ln 3 is some number. I can just leave it like that. Or I could write this as ln 3, 3x. It doesn't matter which way we write it. So they are going to be the same. Okay, so let's look at another one. If you pay attention to kind of what I'm doing, it's not that bad. So we write our function down, ln to the base, derivative of the exponent. That's kind of what I'm going to be doing over and over again. So looking at this one here, y equals 2 negative x to the 3. So what did that say we do? So y prime is equal to write my function down times the ln of the base times the derivative of the exponent. So where did it get these numbers? Remember, this is the derivative of my exponent. And then this one is just ln of my base. Now I just need to clean that up a little bit. So it does equal 2. And there's a few things we can do here. We can get rid of negative exponents as well. So I'm going to kind of rewrite this as negative 3x squared ln 2 over 2x3. So that's just getting rid of negative exponents and kind of moving things around here. Again, I could have this as negative 3 times ln of 2 times x squared if we want, because ln of 2 is just a constant. It is some number. I couldn't tell you what it is off the top of my head, but that's okay. I don't need to. Okay, let's look at another one. Okay, so here you can see again we're combining rules. We have f at x equals 4 to the power of x plus x to the power of 4 all cubed. Okay, so I got a chain rule here as I'm going to be going ahead and working with kind of my new thing, which is the exponential 4 to the power of x. That's kind of my new thing, and I'm using that within a chain rule. So if I want to find my derivative using the chain rule, it says bring that exponent down, write everything as is, subtracting 1 from my exponent, and then timesing that by the derivative of what's inside. So the derivative of what's inside, so we write down my 4x, then we times that by the ln of my base, timesing it by the derivative of my exponent, which is just 1. And then I can look at the second term, so the derivative of x to the power of 4, bring the exponent down, subtract 1. Okay, so there it is. Is there any kind of cleaning up that I can do to this? Well, not really. Again, it looks like I should be able to. And I mean, there's some weird stuff I could do, but really that's how I'm going to leave it. There is no kind of easy kind of simplifying method here, so I'm just going to leave it as that. So let's look at another one now. So y equals x squared times 2 to the power of x. So I have a product rule this time. So my product rule is f prime g plus fg prime. So I got to have that memorized by now, so I'm not going to write it down. So my y prime is take the derivative of the first function, 2x, leaving my second one as is, plus leave my first one as is, times the derivative of the second one. And then that says I got to times that by the ln of my base times the derivative of my exponent, which is 1, so I'm not going to write it. This time there's definitely some common factors here I can take out. So I do have a 2x in the first term, and I have an x squared in the second term. So I can common factor. And then looking at both terms again, there's a 2 to the x in both terms. So I'll kind of underline, this is kind of the first term I'm talking about, and then the second term I'm talking about is this part here. So you can see they both have a 2 to the power of x, and they both have an x I can take out. So I can simplify this one down by taking out an x, 2 to the x, and then what would be left over in the first one is a 2, and then the second one would be an x ln 2. So that's just common factoring out. So if I can common factor out to make it more of in a factored form, that is better in the long run, because when I get to optimization, I want things in factored form. Okay, look at this one. Sorry, sometimes my touchscreen doesn't want to scroll nicely. So we're going to do another one here where we have my f of x is equal to 10 to the power of a radical. Oh, this is going to be a good one. Okay, so f prime at x equals. First thing I'd like to do is write my radical as a fractional thing. So just kind of up here, I'm going to write this down as 10 e to the x minus x squared to the 1/2. That's going to help me when I go ahead and actually take my derivative, because I'm going to have to do the derivative of my exponent, and that's going to make it a little bit easier. So what does my exponential derivative look like? It's write your function down times the ln of the base times the derivative of your exponent. So I'm going to write it down. Times the ln of my base times the derivative of my exponent. So the derivative of my exponent, this is where I'm really glad I kind of wrote it in fractional form, is 1/2 e to the x minus x squared to the negative 1/2. Then I got to times that by the derivative of what's inside, which is going to be e to the x minus 2x. Ooh, okay. Now I'm trying to see, like, is there any common factors here? Like, not really. All I can do is really just get rid of a negative exponent. And I can see I did forget a bracket, so I should go back and add my bracket in there at the end. Doesn't matter really, it's just multiplication there. So I have a negative exponent. So I could be, or I am looking at kind of this negative exponent right there that I can get rid of. Then anywhere else, I don't really have anything I can do. That 2 is already in the denominator. So when I rewrite that, I gotta make sure my 2 is in my denominator. So what does my numerator look like? Well, that's gonna have my 10 e to the x minus x squared, I'll write it back in radical form, times ln 10 times e to the x minus 2x. And that's going to be all over my 2. And then it's going to be the e to the x minus x squared as a radical. Now you could have left those exponents in fractional form if you wanted to. I think it just looks better without fractional exponents. So pretty crazy long derivative. But if I needed to use this, remember, I'd just be subbing something in for x. So I'd still be able to get a nice answer from this. So even though it looks pretty complicated for now, not a big deal. It's very usable derivative. Okay, so now let's look at the derivative of logarithms. And I'm going to actually pause this and upload this one. We'll come back in a second video for this one.